This next section, 15.6, concerns another type of tuning that was done later on. Actually, there was an intermediate stage. All instruments were tuned by the Pythagorean method of jumping by fourths and fifths until about the 12 or 1300s. And about that time, when we had the troubadours going around Europe and so forth, they began tuning their instruments, which were becoming more complex, using the major thirds. And there was two different types of tuning. One used the major thirds as the fundamentals rather than the fifths and the fourths, and it was called just tuning. And then that lasted from about the 1200s until the 1700s. And in the 1700s, Bach came up with a new method of tuning called equitempered tuning. This improved method by Bach, called equitempered, makes all of the half steps equal. And you recall we looked at the piano, and we'll draw the notes on the piano again here. Black note here, none here, black note, and then none here. So this is a C, D, E, F, G, A, B, C. So that's one full octave. And if you count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you see that they're exactly 12 half steps in an octave. What Bach did was say each of these intervals should be tuned equally. Therefore, in tuning these, each one goes by a factor of alpha. So it turns out that each frequency should be alpha, some number, times the frequency below it. So if we call this number, this note here, C sharp should have a frequency. The frequency of C sharp should be equal to alpha times the frequency of C. Then the frequency of D should be equal to alpha times the frequency of C sharp. Frequency of D should be alpha times this one, but that's alpha times C, so this is alpha squared times the frequency of C. So a whole note is a frequency jump of alpha squared, whereas a half a note is alpha. When I get to the octave, I should have done this 12 times. Therefore, it follows that the frequency of an octave up is 12 times the frequency of the basic note, the fundamental. Now, we also know that this has to be twice the fundamental. This alpha is multiplied by itself 12 times. So it's actually going to be alpha to the 12th power. And that's going to be the same as 2 times the basic fundamental frequency. So as I go up, I have alpha times this frequency. This one's alpha times that, or alpha squared times that, alpha cubed times that, until I get to alpha to the 12th power times my fundamental, which has to equal to 2. Now look at this equation. Alpha to the 12th power, this says, has to equal to 2. Therefore, it follows that the number alpha for equitempered tuning is the 12th root of the number 2. And that gives us a number. If you actually take that and work it out, this 12th root of 2 is equal to 1.05946. So to a good approximation, it's about 1.06. And that gives us the frequency ratio of any note with respect to the one beneath it. Now we know the frequencies of every half step. Well, if we have something to fix this, then we could figure out everything. But it turns out we can't. This A above middle C, you recall, is set by musicians worldwide to be a frequency. The frequency that's standard for music is A440. That's the A above middle C. So now, in principle, we can compute all the frequencies. What are those frequencies? Well, if I go down, if I were to go down 1, it would be dividing by this factor. If I go up 1, I'm multiplying by the factor. So if I say, what is the frequency of this C? I would jump from A to A sharp to B to C. That's 1, 2, 3. So I'd have alpha to the third power times 440. And that would be the frequency of the C prime with an octave higher than a C. If I wanted to go down a whole octave from that, I take that divided by 2. Frequency of C then is 220 times alpha to the third power. And now we can move around on the scale going any number of half steps and find any note on the piano and what its frequency is. Now, do these frequencies turn out to be what we would normally want to have for nice integers? Well, if we look at what we end up with, the fact is that this works. A fifth, which is normally a 3:2 ratio by Pythagoras, turns out to be 1.4983. That is so close to 1.5 or 3.5 that you can't discern it. A fourth, which would be 1 1/3, is 1.33. It's not exactly a 3, it's 484. A major third, which is normally the ratio of 5 to 4, turns out to be, that would be 1.25, turns out to be 1.25, but a 9 here, in other words, 1.26. So it's going to sound a little bit sharp in this system. And a minor third is 6 to 5, which would be 1.2, and that's going to sound just a little bit flat. We actually like the fact that the major third is a little sharp and the minor third is a little flat. I have in your notes here what a major 6 would be. It's 5 to 3, which is very close to this equitempered term, and a minor 6 is 8 to 5, which is this term here. So all in all, this tells us that the Bach method is a little bit sharp, a little bit flat in places, but all in all, it allows us to do something we could never do before. We can play in any key, which we could not do until the time of Bach, because we're simply moving in half steps, and the interval ratios of those half steps are the same no matter where we stop and where we end up.